Okay, so this is about thyristors, and if you should watch the videos on thyristors, and so it's a 4-layer alternating PNN material. So all this time we've been either talking about 2 layers or 3 layers. Now we are talking about a 4-layer device, and these are switching devices, so thyristors. So there's 2 categories of thyristors. So thyristors, as I said, are switching devices. They can be open devices or they can be closed. So it's just like a regular switch, except it's electronic. And it's primarily used for control applications. So here's one symbol of a thyristor, one kind of a thyristor. So this is called SCR, and you see it's like a diode, except it has this extra terminal. So this is that 4th layer. Okay. So it's just like a regular diode, except it has this terminal. So remember, with a regular diode, when you forward bias this device, it could conduct. But with a SCR, it won't conduct until you put a positive voltage to this. And this is another kind of thyristor. This is called a Triac. So if you look at this, it will be 2 diodes back to back. So this device conducts only when you have it forward biased in this direction and a gate voltage. This device will conduct in either direction. So for like a AC waveform, this will conduct for the positive waveform or the negative waveform. This one, if you have it connected, plus to minus like this will conduct only during the positive going waveform. So the 3 terminals of this SCR is gate, anode, and the cathode. Gate, anode, and cathode. So if you put a plus voltage at the gate, the SCR will be triggered into conduction mode. And it will conduct as long as that holding current is there. In other words, as long as there is a current going through from the anode to the cathode, this device, once you turn it on, it will keep working. But that moment that threshold current drops, it will stop conducting. So there is 2 ways you can control an SCR. You can actually stop this current right here, right? So if you have this switch open, there won't be a current going through this circuit. And that's called anode current interruption. And the other one is a force commutation. It's like reversing the power from here to here. So bottom line, both cases, what we are trying to do is that holding current to be less than the current going through the circuit. We are talking about SCRs in circuits. So here's AC source. We have a load, we have variable resistor rheostat here, and we have a diode here that's connected to this. You notice that the output of this waveform, this black color line here, it goes only like half of this input voltage. So it stays 0 up to about here, then it suddenly starts to conduct, goes to peak, drops to 0, stays 0 until I hit this again. And this can be adjusted, which point this triggers by this resistance here. So this is talking about reverse commutation, when it will stop conducting. So it's used in a lot of power control applications, primarily like in motor controls. So like VFDs, that's how they work. So in the videos they talked about number of applications also. And motor speed control, so if you ever used to like a variable speed drill, that's how they work. So they're not only motor speed controls like light dimmers and things like that, that's how they work. A lot of people think that like that light dimmers or motor speed controls is just using a variable resistor. It's not true. You can't just use a variable resistor, because if you do that, the voltage that's not dropped across the motor will be dropped across that variable resistor, and therefore the IR square, the power that will be dropped across that rheostat will be so large that you'll need a huge rheostat. For all practical purposes, you could have variable speed controls or like speed controls on motors. Even light dimmers wouldn't really work if we did not have thyristors for controlling of the power. So make sure that you watch the videos. They're very important. I've given the links. So here's a circuit that we are going to build something like this a little later. And you'll notice that here's the input to this oscilloscope. So I'm measuring across from here and here. So be careful with this, because this is not like a regular connection here. You see the plus side, it's going to here, and the ground side is going to the other side of this device. And the purpose of this device, what we are doing here, is measuring the voltage across this light bulb. And we are going to do a couple of labs on this. So I also have a meter up here which measures the voltage. Make sure that when you're putting these meters that you actually make sure that you convert this into AC, because these are AC voltages we are talking about, not DC. I think by default these may come up as DC, so make sure that you change these to AC. If not, you'll get some strange answers. This is obviously enough. It's in series with this going into this resistor through the SCR to ground. So this is an ammeter, right? And this is a voltmeter that's measuring the voltage across this SCR. And the red color line here is this sine wave, which is the input voltage. And this black color line, this white color line here is what's dropped across this lamp. You also remember that by adjusting these cursors back and forth, you can measure the voltage that this is reading. So that'll, if you're talking about this, is channel A, which is the orange color line, orange and black color line. So if you move this, that'll be this channel here. Also, just a reminder, in the assignment, you need to convert this from so this one, if you move this cursor across, you'll be measuring either peak to peak or peak voltages. And if you just move this across from, let's say you put one here and put one cursor here, then you're reading the peak to peak voltage. So you need to divide that by 2 and multiply that by 0.707 to get RMS voltage. Because the assignment talks about RMS voltages, so make sure that you change those to RMS voltages. If not, all of your numbers will be off. The other thing to remember is that if you add this voltage here and this voltage here, you will get something pretty close to this voltage. Okay. Now they're slightly off, obviously enough, but it's quite close to this number here. And this is, of course, if it's reading this number here, that's 152 milliamps. Okay, so be very careful on these two slides. This is, I think, slide number 7, and the other one is slide number 8, because this is measuring across this device right here. Because I have put this black color line here and the orange color line here. Okay. And you can change the point that this fires or turns on by adjusting this resistance. So this is the other one that you notice the connection right here is here, and then this is connected to ground. So the previous one, it was not connected like that. Okay, so watch when you're doing this, the assignment, that you keep track of this. So what this actually, this blue color line is reading is that voltage across this device. It's not reading the voltage across this lamp. Okay, it's kind of common. It's a misconception. It would be wrong to assume that this blue color line is reading this voltage. It's not. It's reading this voltage. If you move these cursors, you will see that it's coming close to this number right here. Again, remember, you have to multiply these numbers via peak-to-peak value. I mean, it depends on where you put the cursors, of course. But if it's a peak-to-peak, you have to divide that by 2 and have to get a peak value and then multiply it by 0.7 to get RMS value. So the assignment talks about RMS values. It's not talking about peak-to-peak values. Now, in the assignment, it talks about what is the voltage across this lamp. So you can use this number. But obvious enough, you can't use these numbers for that. Okay? Because the oscilloscope is not reading those numbers. Also, the second part of that assignment is to replace this oscilloscope with a Tektronix oscilloscope. So that's kind of the reason I did that is that we need to kind of refresh our minds about using the Tektronix oscilloscope. I hope everybody is reasonably comfortable with that. So here, this resistance is 71%. So I know that this, by just looking at this device, I can tell that this is an open switch, because it's 120 volts, right? And that's pretty close to this voltage here. You'll notice that this voltage is 0 volts, and you have almost no current going through this circuit. But if you look at the blue color line, it's a full sine waveform, right? And what that is saying is that the voltage from here, from this blue color line to ground, just this number here, this connection here, which is equal to 120 volts. So another type of device is a DIAC, which is a back-to-back diode. So it will conduct in both directions. Remember, the regular diode only conducts only in one direction. This one will conduct in both directions. And of course, to make it conduct, you have to overcome the threshold for, whatever, if this is silicon diode, 0.7 volts or something close to that. So TRIAC is two diode devices. It's a SCR back-to-back, like this. And the advantage of it is you get an output on both sides. So you get output here, you get an output here. With the SCR, because it won't conduct in the opposite direction, you will only get this part here. You won't get this part. So that's the difference between a TRIAC and a SCR. But they work exactly the same way. You have to latch it to turn it on to make it conduct, and once the current drops below the holding current, it shuts off, which is this number here. Okay, so here's a circuit using a TRIAC, and you'll notice that I get a output waveform on the positive going waveform and the negative going waveform. So obviously this device is much more efficient, but it just depends on what your application is, whether you need SCR or TRIAC. So here, it's just looking at the voltage here, I can say that this device is shut off, because this voltage is equal to this voltage, and the current is 0. And just looking at this one, I can say that this device is turned on. Well, obviously this light is turned on too. You don't need to read anything here. You can just look at the light bulb. And here you can see, the light bulb is off, so it's turned off. So that's SCRs and TRIACs, and make sure you watch the videos and complete the assignment and the table. Careful about on slide 8,